displacement time graph, this is the velocity time graph, this is the acceleration time graph. So if I run this animation in slow motion, we can see that the velocity stays constant, indicated by the red arrow, whereas the displacement is increasing. Notice we've got zero acceleration. That means that the speed is not changing over a period of time. The speed remains constant. Let's have a look at a simple acceleration graph. So now we've got constant acceleration. The velocity gradually increases, and the displacement time graph shows the slope gradually increasing. This indicates an increase in velocity. Let's play the animation. So notice the acceleration remains constant, whereas the speed is increasing and the displacement increases. Let's look at a simple deceleration. So in other words, this is like putting the brakes on. So we've got an initial speed and we're going to decelerate to 0. Notice when we decelerate, the acceleration is in the opposite direction to motion. Notice the velocity gets gradually smaller. Notice how the acceleration is shown underneath the curve. Let's look at a rise and fall situation. Let's play the animation first. This simulation is like throwing a ball up into the air. Notice that the acceleration indicated by the blue is in the same direction downwards. So when the motion's going upwards, that has the effect of slowing the ball down. When the motion is downwards, that has the effect of increasing the speed of the ball. If we take a look at this graph, we can see that we've got a gradually decreasing slope, indicating getting slower. At this point here, we've got zero slope. In other words, it's a bit like a flat line. That indicates zero velocity. And gradually the slope decreases in a negative way. That indicates that the velocity of the ball is increasing, but in the opposite direction. Let's have a look at a ball falling and then rebounding. We'll play the animation first. So notice constant acceleration. Right. As the ball hits the ground, notice we get this rapid change of velocity in the opposite direction. That's because when the ball hits the ground, we've got a force pushing the ball back upwards. That's why we get, for a fraction of a second while it's in contact with the ground, a positive acceleration. Once it's left the ground, the only force that's acting is the force due to gravity, which is always downwards. So that's why we have a negative acceleration. So we'll play the motion again. So velocity increases, then decreases. And these are the shapes of the graphs that we get from a ball bouncing. Finally, let's take a look at what we can do. Here we've got lots of different changes in velocity. Watch what happens to the motion. Increasing, opposite acceleration, etc., etc. Play that again. Notice the changes in transition of the acceleration time graph. Notice when we've got a negative gradient, we've got a negative acceleration. Negative gradient, negative acceleration. let's do our own shape of graph. Okay, so what we've got here then is increase in velocity or constant acceleration. Then we've got no acceleration or constant velocity. Then we've got deceleration, which is indicated by a negative acceleration. Then we've got zero speed for a while. So at zero speed there's no acceleration. Then we've got an acceleration, then a deceleration, indicated by the positive, followed by the negative. Let's play the animation. Notice how when we've got zero velocity, the displacement time graph is flat. So that's how we interpret velocity time graphs and displacement time graphs and acceleration time graphs.